Alright, today we're going to do some integration work. We're going to look at the area bounded between two curves, the region bounded between two curves. So I'll give you a second to read the question. You guys can kind of read what's there. Let's pause it, read it, draw a little arrow pointing up to it. While I struggle to do that, there we go. Alright, let's start. On the same plane, we're going to sketch this curves y equals x squared and x equals y squared. Immediately, we're presented with something unfamiliar, and that's this thing right there. How could I write that in terms of y equals? Well, to do that, I'd have to get rid of the squared. And what is the opposite of squaring something? It's the square root, which is what it ends up being. So if we remember what we looked at before, this right here, this curve is actually a semicircle, is what it ends up being. Sorry, it's not a semicircle. What am I saying? It looks like this. Kind of goes off in that direction there. So what we can do here is we can take a look at plotting both these curves. So we've got our first curve, which is the parabola, y equals x squared. And then we have the second curve. Oh my God, I'll screw this one up. Which is that curve right there. So we've got two of them. This is what it ends up being. Now, the reason this isn't plus or minus is because the curve x equals y squared is actually that right there. That's what the curve actually ends up being. But we are literally looking at the intersection, so we're not going to be including that one. And writing it as y equals actually changes what we're going to be doing and the fundamental way we look and we view, it's a bit of fluff on my iPad, and the way we look at this graph here. That's the area we want to shade. That's the region we want to be looking at between the two of them. That right there is going to be my point of intersection. Now, how do we find the point of intersection? Well, we would make the two curves equal to each other. They're both equal to y. X squared is equal to the square root of x. Looking at this, we need a value where both x values are going to end up being the same. In terms of solving this can get a little bit tricky. It can be a little like, I don't really know what's going on here. But the best way we can look at it is the x value is going to be 1. There's really not much else it can be. And it can also be 0, of course. But other than that, if we look at the values of our curves, it's only going to hit at those 2 points. We know one of them is the axis, and we can look just by inspection that the other one is going to be when x is equal to 1. And that's something we really obtain when we look at the graph and think about the value of what is happening. X squared, the square root of x. One's going off in the other direction. We could try a value like 2 or 3, but we see pretty quickly that it's not what it's going to be. And then we're actually going to integrate to find it. Now we need to be thinking about what curve is above and what curve is below. And if I drew these with a bit of color, this curve here, y equals x to the half, or the square root of x, that's above. So we have that area between there, and we're going to subtract the area of the black curve, which is the one we just found, in order to get that black shaded region right there. So my integration, my integral is between 1 and 0, and it's of the square root of x with respect to x minus the same between 1 and 0 of x squared. Now, this is very similar to what we've got above, but not quite. But we remember what we learnt before about our fundamental theorem and about integration, that if we're integrating between the same points, we can combine them under the same integral. And we end up with something lovely like this. Now, we need to find out what the region is. Let's integrate it. This is x to the half. Always, we want to be writing with a number power or fraction power, whatever it may be. Let's integrate, add 1 to the power, 3 over 2, divide by the power. I'm going to keep it as 3 over 2 just for this point. Add 1 to the power, cubed, divide by power 3, between 1 and 0. Remembering that when we divide by a fraction, how we can rewrite it by flipping it over 3 minus x cubed over 3 between 1 and 0. That would be because we have x to 3 over 2 divided by, 3 over 2. Remembering how we divide our fractions, it ends up looking like this. Just a little quick little tidbit over there. And then substitute our values in. And the area for that is going to be 1 over 3. I don't really need to put 0 into here. I can do it anyway. Minus 2 times 0 over 3 minus 0 over 3. We end up with just a third. And essentially that is, sketching areas and sketching graphs, and finding the areas between them.